we saw these amazing talks about machine learning. You saw videos and beautiful presentations about what can be done. Now, we have to put that aside, and we're going to talk about what cannot be done, okay? This means there will be no videos, sorry. There will be some math, sorry. So let's go. We're going to talk about fine-grained algorithms and complexity, an area that I have been working on in the last 20 years. Okay, good. So let's look at the central question of algorithms research. It is, how fast can we solve fundamental problems in the worst case? So this is the question you see in a lot of textbooks when you open them. Let's unravel this a little bit with some math. Okay, so you all know what computers are, but for me, computers are mathematical, so they're mathematical objects. We have various reasonable models of what a computer is. It could be a Turing machine, it could be a random access machine, a pointer machine, there's many models. What do these models give us? It tells us some basic operations that take a unit step to perform, a constant time operation, something like, let's say I have some numbers stored in a word of memory, I want to add two numbers, that's one cost, one unit cost. I could subtract them, I could move a pointer from one place to another in memory, that's the unit cost. And what we want to compute are some problems, like for example, I give you a network and 2 points in the network, what is the shortest path between them? Now, formally, all these problems are just functions from bit strings to bit strings. So you can encode your network as a string of bits, and the shortest path you output is a string of bits. I personally don't work on problems that are not computable. There exist problems that cannot be computed by any machine, but we will work with ones that are computable, so you can think of there being some search space of solutions, and you can go through the search space that gives you a way to solve them. Now, what is an algorithm? An algorithm is some program you can write on your machine. But what is the machine? Is this model that you picked, the Turing machine or whatever. So you have some algorithm. It takes an input, which is some bit string of length n, and outputs the value of the function on that input. All right, what do I care about? I care about, the running time of the algorithm. The running time of the algorithm, for a particular input, we know what it is the number of steps in your computational model that the algorithm needs to perform. But I care about the asymptotics. So if I fix the length of your input n, and the problem you want to compute f, and A is the algorithm, the running time on input n is the maximum over all possible bit strings, all possible inputs of length n of the running time, the number of steps in your model that algorithm computes. And I don't actually care about the exact number of steps. I care about how the running time grows as your input grows. So as the bigger and bigger inputs you pick, the bigger and bigger graphs you pick, I want to know what the running time will look like. And what is the best I could hope for? The holy grail is a linear time algorithm. Remember that when you have an input, you have to at least read it. If you don't read the whole input, you might miss some information that is really necessary to compute what you're computing. And so you need n steps, where n is your length of your input. But I'm okay with like 10n or 5n or something like this. And this is what this order n means. And so this is what we want. And there's some good news. There's all these techniques that have been developed over the ages. There's convex optimization, matrix multiplication, dynamic programming, and so on. There's a lot of algorithmic techniques out there, and you can solve a lot of fundamental problems super fast, maybe in linear time. A long time ago, in the 1950s, Kurt Gödel was thinking about the problem of exhaustive search. What is exhaustive search? Well, I told you I care about problems that are computable. So there is some search space. And there is this algorithm that depends on the search space, just enumerate all solutions in the search space and figure out if there's one, the best one, right? That's the exhaustive search algorithm. And Gödel said, I want to know in general, how much can we improve over this exhaustive search? And we still don't have the answer for this. For many fundamental problems that we really, really want to solve, the best algorithm that we currently have is essentially the exhaustive search one. And it's really frustrating. And I study the question of why that is. So there's a lot of these hard problems on which all of our known techniques get stuck. They're very important. They come from all over the place. Their best known algorithm, as I said, could be the exhaustive search one, or maybe it's some algorithm that you get by combining known techniques that you find in textbooks. And these are the textbook algorithms. And if you go on and on, so you see that they're super slow, and you can go in the literature, you can go and look on archive and so on. People have been working on these algorithms on these problems for decades, and there have been no significant improvements. And you wonder why. I will give you 2 examples of such problems. Here's the canonical problem. All right, what do we have? We have n variables, x1 up to xn, okay? And you have some formula. It looks like something like this. So you have these things in the brackets, they're called clauses, and inside the clause you have a variable or a negation of a variable or another variable, and then an and with another clause that has the same form. And given this potentially very long formula, you want to know, is there a way to pick values for these variables? What are the values? The values are true or false, 1 or 0. And when you want to pick a value for every variable so that when you plug in the values and you evaluate the formula, you get true. So for example, over here, if I set x2 to false, not x2 is true. So this entire thing is true. And over here, it's also true because not x2 becomes true as well. And no matter what I set x1 or x3 to, I will get a true thing. So there exists some assignment. Now, in general, it wouldn't be as easy to pick an assignment that satisfies the formula. And what is the exhaustive search algorithm? I look at all my n variables, and I try all the possible 2 to the n ways to assign truth values to the variables. I say, let's try if x1 is true, x2 is true, x3 is true, and so on. Does that work? No. Okay. Then I try x1 is true, x2 is false, and so on. I enumerate all the possible 2 to the n options, and I check, I evaluate the formula, and that gives me an algorithm, the exhaustive search one. But 2 to the n is horribly, horribly slow. So we want something better. And the best people have been able to get is something like this. There's this 2 to the n, and in the exponent there's a little bit of savings. C, let's say, is 2, some constant independent of n and k. K is the length of the clauses. Over here, k is 3. So this thing times m is the number of clauses to some other constant like 10. Okay? And this is some running time that's a little bit better than this 2 to the n that I had over here. But unfortunately, as this length k grows, instead of 3 literals per clause, I have, let's say, 100 or 1,000, and so on. This savings is so negligible that you basically get the 2 to the n algorithm. And this is what's frustrating about this problem. It is used all over the place. You may have heard of SAT solvers used in formal verification and all sorts of things. You need to solve this problem, but in general, there's no algorithm known that can do much better than the exhaustive search. All right. So what makes this interesting to me is that 2 to the n is the easy thing to do, but there's nothing that is like 2 to the n to the 1 minus epsilon for epsilon bigger than 0. Nothing like 1.9 to the n. Here's another problem, a little easier, but still hard, okay? I have 2 sequences of letters. They're over some alphabet like A, C, T, G, and I want to find a sequence that appears in both of my input sequences and has maximum length. What is that? Well, I can just spread them out, and the blue letters is a sequence that appears in both of them. Okay? If the sequences have length n, I want to have a running time that's as close to linear as possible. This problem has a lot of applications. For example, you may have 2 sequences that are DNA sequences. You want to know how similar are they. And this is a notion of similarity, some sequence that appears in both, right? Or maybe you have a bunch of misspelled words and you have a dictionary and you want to find the real words that correspond to the misspelled words. So that would be an application of this. And this is solved a lot of daily on very long strings, but the textbook algorithm is quadratic in n. Now, if your n is 10 to the 9, quadratic is 10 to the 18, which is super slow, and no one will want to run such an algorithm. Why isn't there a much faster one? Why isn't there a linear time algorithm? The best known algorithm saves over this n squared by a tiny bit. It was invented in the 80s, and there has been no improvement since then. In general, we do not know an algorithm of this form, a running time of this form. Okay? What do these two problems have in common? They have some running time, t of n. It has stood there forever, pretty easy to obtain, but we cannot get anything better than t of n with an improvement in the exponent. Okay, so here we go. Hard problems are ones where you can get a textbook algorithm very easily. It's pretty slow, and we don't have any improvement over this textbook algorithm, even though we worked on it forever. I want to know, why are we stuck? These problems are very different. Why are we stuck in the same way? And are we actually stuck for the same reason? Could it be that these very different problems, one with an exponential running time and one with a quadratic running time, actually are the same problem in disguise? Maybe they are. We'll never know. So that's what I've been working on. What I'm going to tell you in the rest of the talk is I'm going to tell you a little bit about some traditional hardness and complexity theory. Then I'm going to tell you the new complexity theory, the fine-grained complexity theory. Okay. Traditional hardness. Here's one sort of hardness we know how to prove. Fix any computational model you like, Turing machine, random access machine, whatever. Usually we can prove a theorem of this form. There exists problems that can be solved in n to the c time, but provably do not have a faster algorithm. N to the c is the correct running time for these problems. The problem that we have here is with the word here exists, okay? What we want to show is that our favorite problem, like SAT, doesn't have an n to the c minus epsilon time algorithm. And the current techniques in complexity theory don't even allow us to show that KSAT is not in linear time, the problem where we cannot solve it better than 2 to the n. And there's a huge gap between 2 to the n and n. All right. Here's another hardness in complexity theory. This is the P versus NP question, if you've heard about it. All right. This is one of those famous questions, Claim Math Institute Millennium problem. If you happen to solve it, you get $1 million, and you're famous, and so on. All right? Everybody, for some reason, believes that P is not equal to NP, and we base all of modern cryptography on that. We need it. What is that? It's P are all these problems that have algorithms that are polynomial, like n to the 10, n to the 100. There's a lot of these problems. And NP are those problems for which, given a solution, you can verify that it's a correct solution quickly. But just because you can verify that a given solution doesn't mean you can find one quickly. So this is why we don't know whether P equals NP. And one of the things that was proven in the 70s is that this problem KSAT that I told you is what's known as NP-hard. And this just means that if you can get a polynomial time algorithm, like order n to the 1000 time for KSAT, then P would equal NP, and this is something no one believes for some reason. And so you can think of this as conditional hardness. Let me explain conditional hardness. If you have a problem Q like SAT, what is NP hardness for that? Well, you assume this thing, P not equal to NP, that everybody believes. Then you perform some mathematical task, which is to show that if Q had a polynomial time algorithm, no matter what your polynomial is, n to the 1 million, then that algorithm can be used to solve any problem in NP in polynomial time, and therefore P would equal to NP. And because we assume the opposite over here, we'll get a contradiction. We'll get the Q must require super polynomial time. That's the hardness. So you can use P versus NP to show that our favorite problem, KSAT, probably doesn't have a polynomial time algorithm. Okay, this is great. However, remember the LCS problem? That one had a quadratic time algorithm. That's polynomial. That problem cannot be NP-hard unless P equal to NP, because this part over here is already satisfied. So you cannot perform this step here if you believe P not equal to NP. So NP-hardness cannot be used for problems that are already solvable fast. Well, you know, quadratic time is not that fast, but it is not super polynomial. So NP-hardness is great, but it's not fine-grained. It's too coarse-grained. Now let me step back. You know, if I asked you, if you have an algorithm that runs in n to the 1 million time, or n to the 1,000, is that fast? Is that efficient? No, it is not. If n is a million, you know, n to the 1 million, then you apply to a million, and a million is way too big. No one would ever run an algorithm like that. In fact, I would argue that for most application, you wouldn't even run a quadratic time algorithm. But yet, in theoretical computer science, if you take a course in that, you will hear this polynomial time that's efficient. But that's not why we use polynomial time as a notion of efficiency. It's for other reason. Because, for example, we can forget about the model of computation. Remember I told you about random access machines, pointer machines, whatever machine model you come up with, you can translate between them with some polynomial overhead, and that's why polynomial time is useful. Or if you have an efficient algorithm that is using subroutines as subroutines, polynomial time algorithms, you want that thing to also be efficient. And nicely, a polynomial of a polynomial is still a polynomial, so efficient stuff using efficient stuff is also efficient. But that's not what we care about. Right now, I'm going to abandon this notion of efficiency. I will care about the exact running times. And I will try to build a notion of hardness that is like NP-hardness, except now it's so fine-grained that it actually cares about the running time. All right. Let me try to quickly contrast the two approaches, and I'll tell you what it is. Here's what I told you about NP-hardness before. You assume something P not equal to NP, which happens to be equivalent to SAT requiring super polynomial time. You have something called a polynomial time reduction, which shows that if Q had a polynomial time algorithm, then everything in NP does, and so on. And then you conclude, then therefore, because this contradicts the assumption, Q must require a lot of time, super polynomial time. But now what I'm going to do is I'm going to do something completely better. I'm going to change the hardness assumption. I will pick some problem I think is hard, like SAT, and I'll pick its best running time, let's say 2 to the n. So let's say problem H is hard in the sense that it requires H of n time on my favorite machine model, random access machines. Then I will have something called a fine-grained reduction, which instead of using a polynomial time algorithm for a problem Q, it says suppose Q had a better than Q of n time algorithm, and then the reduction will show that this hardness hypothesis is violated, so that the problem H that I thought required H of n time, using this fast algorithm for Q would now be able to be solved faster. And so I would get a contradiction showing that under this hardness hypothesis, Q must require a lot of time, Q of n time, not super polynomial necessarily. What problem should I pick as my initial hardness hypothesis? Well, I already said SAT is hard. So I'm going to use a hypothesis that says that SAT is super hard. And there is such a hypothesis. It's called the strong exponential time hypothesis, because there's some other one that's called weak exponential, so we'll forget about that one. So Seth, it's called Seth, and it basically says SAT requires 2 to the n time. There is no epsilon for which you can solve all the KSAT formulas and 2 to the n to the 1 minus epsilon time. Let's assume that's the case, and we'll just use that as a hardness assumption instead of P not equal NP. And this is much, much stronger than P not equal NP. P not equal NP just says, oh, SAT only needs super polynomial time. here I'm saying not only is it super polynomial, it's 2 to the n. Okay, it's much bigger. And there's other hardness hypotheses you can pick, but this is one of the most famous ones. After you have the hardness hypothesis here, SAT requires 2 to the n time, you need to have some notion of reduction, which is to show that if some other problem, like the longest common subsequence, can be solved faster, then you can solve SAT faster. Here's what polynomial time reductions are. They're translations between problems. Let's say I have a problem A and I have a problem B. A polynomial time reduction takes an instance of problem A, runs a polynomial time algorithm, and spits out an instance of problem B. Now, this instance of problem B can be polynomially larger. I don't care. What I care about is that the answers of A and B should be the same. And here, they're decision problems, meaning that the answer to both problems are yes or no. So this is what a polynomial time reduction gives us. Let me show you, it has a bunch of weaknesses. For example, because I insisted the answer has to be the same for both A and B, you cannot reduce a problem such as shortest path, give me the shortest path between two nodes, to a problem whose answer is only yes or no, because the answers have to be the same and a path does not only have one bit. This can be fixed with something else, something called the Turing reduction. What cannot be fixed is this fact that we care about arbitrary polynomial times. And this is what we got to fix now. So this is a notion that we define in 2010. Let's say I have two problems, A and B, SAT and the longest common subsequence problem. And we have two running times, little a and little b, 2 to the n and n squared. They're two different running times. So now, you can forget about the text right now. Look at this picture. The reduction takes any instance of the hard problem A of size n, runs an A of n to the 1 minus delta algorithm. A of n is the running time for problem A, produces many instances of problem B. They could have different sizes. Their number could depend on n. And once you have the answers to all of these, you would get the answer for A. The important thing is this inequality, and I'll have to explain this in the following way. It's just to show the following thing. If A has a reduction to be like this, and B can be solved fast, and B of n to the 1 minus epsilon time, then A also can be solved faster than its A of n runtime. How do you solve it? Well, B can be solved faster, so you run the reduction and then apply the fast algorithm of B over here. And the running time for solving all these instances of B is just the summation of B of n sub I to the 1 minus epsilon. That's the running time here. And because of this inequality, it's less than A of n to the 1 minus delta. And when you compose it with the algorithm that spits them out and solves the problem, you get an A of n to the 1 minus delta time algorithm for A. And it has some other properties like transitivity and so on. And it's extremely useful. Okay, so we use this notion of reduction here, and then if the reduction exists and the problem H is actually hard, then we also get hardness for the problem that we care about, but with this other another runtime. Let me give another parallel. So over here in 1972, Karp showed that a lot of problems, 21 problems, are NP complete. Meaning that if you can solve any of them faster than any of them in polynomial time, then you can solve SAT in a polynomial time, and therefore every problem in NP in polynomial time. And since then, thousands of other NP-complete problems have been found, thousands and thousands every day. And some problems that are not in NP are also hard, many of them. So we have a very, very beautiful picture, and it's very useful because let's say someone says, I want to solve this problem, and I tell them, oh, it's NP hard, and they can say, oh, well, now I think I should be using heuristics, or I should approximate, or maybe I should redefine the problem so that now it's easier to solve. What can we do in our fine-grained world? Well, you can take these three problems. I only defined one of them, this one, Seth. And you can show that if you assume that SAT requires 2 to the n time, then a huge number of problems actually require quadratic time. You will not be able to get an algorithm, a linear time algorithm, or one that's n to the 1.9 for any of them, for LCS, for the diameter of a graph. Even approximating the diameter of a graph is hard. Many of these problems require quadratic time. Sometimes we get equivalences. This problem is called all pair shortest paths, is equivalent to a lot of problems in cubic time. This problem implies a lot of hardness for problems in geometry and sequence alignment and so on. So we can actually get hardness about different running times and sometimes equivalences. All right. Using other hardness hypotheses, you can get more. And this is the entirety of my talk. Thank you.